right now at this panel discussion, there's not really a common theme like the other panel discussions other than we're all here together at the same conference, and a lot of these topics are, I believe, of importance. Victor is here presenting about the deuterium depleted water, which most people have never even heard of, that this is even an issue or that there's anything to it, because nobody's ever heard of it. But, very, very few people. And so it's a very important concept. I've been intrigued about it since several years ago at the Tesla Tech conference, and I'm very happy he was able to come up here and be able to present. And I hope you found that this audience was very receptive to what you wanted to share.
Phenomenal. Thank you for inviting me. It's been a great experience.
And then Jennifer, on a very different related topic, is Off the Grid. But the second book we ever produced for A&P Electronic Media was Save on Home Energy, and it was all about how to reduce your home energy costs. And so, insulation and weatherization is not as sexy as fractal discharges showing the life forces in the ether and that kind of thing, but it's very important, and it's very underappreciated. And that is actually where most people need to start when they want to look at reducing energy costs, is weatherization, insulation, these radiant barriers, because if the average home loses half the energy that it's using, and the average or the most expensive expense for energy in the average home is heating and cooling, well, you want to keep on you want to keep what you make, and you want to keep out what you don't want, and that's where you start, because people just want to put solar on a home to just waste half of it. Well, if everything is kind of tightened up, you actually don't need as much as you might think. And what Jennifer and her husband Terry has shared with their experience, they're 100% off the grid. Mm-hmm. They're doing it, and I can't wait to see what's going to be coming out down the road once you do some of the other modifications with the batteries and the heating system and all this. And so thank you for sharing and doing this at the last minute when I asked you about it less than a week before the conference if you could present. So thank you very much, Jennifer.
Thank you for having me.
Yeah, thank you so much. And then, thank you. And then David and Bruce on the stellar transformer concepts, which is also a very different concept, but one that is actually ties in with quite a bit of the work going on here. And so thanks for coming up and bringing some of your associates who have other pieces of the puzzle to put together. And I'm looking forward to the collaboration that both you guys and some of your other associates are going to be having with Griffin and Eric Dollard. And there's a lot of things that are really going to be very interesting, coming up with all of this. So, hey, thank you so much, Bruce and David.
Yeah, thank you.
Thank you so much.
Great. Really enjoyed it.
So, start off, do you have any comments just about what you're doing, the conference, where you're going after this with your company? And
well, this is an energy conference, and so I was thinking about, you have external energy and then you have human energy, and how do they relate? So do you know how much energy a person uses? So if you take I'll tell you, I don't know, maybe you do know, but
I would guess 100 watts. I think, wasn't that on the matrix?
If you daily, it's 58,000 watts, 58 kilowatts. If you take the entire per day, if you take the entire population of the world and you divide it by or you take the amount of energy that's made and divide it by the amount of people on there, it's 58,000, 58 kilowatts. And how much can a person make? When they're 100 watts, maybe 400 watts at peak. So we actually require 600 times more energy than we produce. And this is why we're all here, right? Because we want to bridge that gap of how do we go from 100 watts to 58 kilowatts. So deuterium depletion, deuterium depleted water, the goal of it is to increase energy in the mitochondria and how oxygen is utilized in the body. So if you do that and you increase the health of somebody, what kind of impact does that have on the family, on the community, on the planet in conservation of the energy that we need? Looking at it in more of a macro scale as we move forward. So consider we have something that's a new standard in water purity. It'll take a decade or more, who knows how long, until this is widely accepted. But then this is the promise, to increase our own ability to produce energy so we can conserve the energy that we need from external things, or maybe utilize that energy into projects like we're trying to create, like everybody here is trying to create, in bridging the gap between the 600 times more energy that we need than we can actually produce with our physical body.
And do you want to share what your website is again and how people can get a hold of
Yes,
you? And
it's drinklightwater.com. And
that's
light-
L-I-T-E.
L-I-T-E, yeah. L-I-T-E version of light water. And our goal is to get more people drinking light water and sharing the experience of deuterium depletion, get themselves down by 20%, get the burden of deuterium out of the body at least when you take 20% down. Incredible things start to happen physiologically for your health benefit. And our goal is to build a factory here in the United States, which we're actively started already, and just keep on spreading the message of deuterium depletion and how you can lower your deuterium levels.
Are you able to share where in the United States that?
We're not,
place?
well, I can't share where the pilot is right now, but where the final factory is going to be is going to depend on a couple key factors. One, you want to be in a place that has already a water aquifer that's already slightly deuterium depleted, because the less it is, the less energy it costs. So, and you also want to be in a place where you're close to energy. And in our case, I mean, the energy could be anything, but obviously natural gas is the most efficient that we can use right now until somebody makes us a anybody?
Well, you know, in Washington State, there is some areas that have some of the lowest energy costs in the nation. There's Microsoft server centers. There's Bitcoin mining operations, and a little bit up north, it's super, super cheap.
Yeah, Wyoming is also good because they have water that's lower in deuterium, and they have a lot of natural gas. So
Wyoming.
yeah, Wyoming is looking good. Yeah, but it could be Nevada, it could be Arizona, it could be Washington. But yeah, we're not sure yet. But the pilot facilities on the East Coast, close to industry. Yeah.
Thank you.
Yep.
Jennifer, any general comments and your experience at the conference? And
This has been the best week off ever. So first of all, that was really, really fun. And I've learned a lot, and there's so much I don't know, and I think I will learn from Parker and read a lot more. Get Peter to give me some more insight and bring him out to help us right-size our battery. And just hopefully come back next year. It's been great.
have you ever thought of having a YouTube channel or a website where you kind of put out a blog and kind of give a timeline of all your updates and everything like that?
I have never considered it. I'm probably not a great candidate for that kind of thing. But maybe, I don't know.
Okay.
Hadn't thought about it.
Okay. Thanks, Jennifer.
Hmm?
And David or Bruce? David and Bruce?
You can start, Dave.
Oh,
You wanna talk about Argo's view?
Oh, okay. Thank you once again for having us join, and thank you, Bruce,
Sure. Thank you.
for bringing me along. And we've kind of been walking this pathway for really since like 2015, but now it's starting to manifest. And there's just it was very synchronous today to have the I forget the guy's name, but for the Sapphire Project connection. Because we've all been kind of on that same path, and there's kind of a would you call it, like a meeting of forces and coherency happening that we can sense. So, but this whole event has certainly been part of that. So, thank you.
Awesome.
Really.
Thank you.
Yeah, I could add to that, in the Sapphire Project where they show the little buds, the anode tufts in that. Oh, hello, can you hear me? Okay. These anode tufts that form in the star in the jar for the Sapphire Project and stuff. The guy we've been working with in Italy, his theory talks about how those form, and they're the vertical tidal dynamic of the induction effect. It's a vertical induction effect tied to tidal, and those anode tufts are the active components. And then flip that up a little bit. There
That's
we
good.
go.
That's
Okay.
good.
So that flows with our theme, the stellar transformer. The core effect is these sea urchin spike type. They look like the anode tufts in the sapphire, and they're responsible for this separation of the tetrahedron, the uniform distribution, that's what it's caused by, but because the anodes repel each other, so it gives you a nice geometric configuration. And that stretches up into the layers, the other duality of layers as you go out on the double layers, that vibration changes to the other geometric dualities as you go outward, on the Earth, we think. So we're looking at that as part of our theory for understanding how the Earth works and extending that to the other planets and the sun. And so that's what the theoretical aspects. The practical things that we're doing is looking at forecasting earthquakes primarily is our focus now, and also the other natural disasters associated with this, the hurricane links, the wildfire relationships tied to coronal mass ejections. So all these things we want to really deep dive down and try to figure out how to look at the sun, understand how it's going to affect the Earth, and come up with some algorithms based on some data streams that we can process and analyze and develop some algorithms to develop a forecasting scheme. So that's our long-term goal, and we're starting out with looking at the earthquakes there in New Madrid.
And what is the website, and how do people learn more?
Okay, we have a few for the nonprofit is geoplasmaresearchinstitute.org. For the business spin-out that we're working on is stellartransformertechnologies.com. And then our journal, where we do a lot of our publications, is New Concepts in Global Tectonics, represented by ncgtjournal.org. I'm sorry, no, that's a .com too. So those are our three go-to sites.
Are there any questions for deuterium-depleted water, off-the-grid, or stellar transformer concepts? Come on, Jeremiah. I know you're wondering about something.
We've got a question online. Is there a process for removing deuterium from water? Deuterium, excuse me. That was the question. I
That's
think
it?
the answer is yes.
Yes, yes.
What kind of process is there for removing it from the water?
It says, is there a process? So I would refer them to a
The one we use
presentation.
The one
yeah.
we use is rectification distillation. That's the most efficient process. It's the one that gives you the most concentration of removal. So it allows us to have what's known as super deuterium depleted water or super light water, meaning it's below 25 parts per million. There's other processes. I don't think they're as good, but there's there's ways to get deuterium out of water. The body does it, you know. That my whole presentation was about how our bodies try to filter it, but we keep getting overrun. So, and that again, that if you reduce the deuterium burden in the body just by a little bit, 20%, then the natural processes that we have can kick in and actually keep us healthier longer. Otherwise, we just get overrun too quickly. From the time we're born, you know, it's in everything. So.
Then a question, what...
I have
go ahead.
a question that goes with this. So the process, and what do you call it again?
Rectification distillation.
So most people know what distillation is, heat water, kind of steams out, leaves
it's a
the
type
heavy
of
stuff
fractional
form.
distillation. So it's just like you get oil.
Kind of
You have
a
to-
alcohol still
Yeah,
type process,
yeah.
but a lot more
It's more
Preci-
it's
precise,
more-
precision.
Yeah, it was developed at the Institute of Fine Technologies in Moscow originally. And then my colleagues actually made it into a commercial production. It took a long time. But yeah.
All right, so then there's a question, what really drives the tides?
Oh, is that?
Really?
Oh, if it's not gravity, what is it? Okay. Well, we would go with an electromagnetic driver. Oh. Pull it out. How's that? Stretch it. There we go. Yeah, I'm not gonna. We're gonna say planetary bodies in the sun.
So gravity?
If you want to understand gravitational as an attractive force, maybe driven by electromagnetics, that's kind of how we view it. Gravity is a measurement in the vertical. That's how it's defined. I took the measurements for years. And I was unaware that it was more likely electrostatic charge attraction. The way we look at it, the core is positive. The mohoveric discontinuity, which is kind of the deep part of the mantle, and the ionosphere, positive, positive, positive charges. No charge, no charge, no charge. You know, you want to think of it as a negative versus positive. It's better to think of it as charge versus no charge. More like Walter Russell conceived it, we think. And that way you can understand it's just a differential of charge that drives all the activity between the layers, the capacitance layers, you might think of them that way. That's kind of our approach. It may not be the exact right one, but we're going with that and see how it works.
Any more online, Bruce? Stephen?
So all of these turn of the 20th century ideas are coming back.
Right.
Yeah, exactly.
Seems
All these
like that.
old technology, well, understandings. So I was thinking that you probably have a lot of heavy water as a waste product.
We don't.
You don't?
We don't, because, as I mentioned, most of the water, the deuterium is locked up as HDO, not as D2O.
Okay.
So 1 out of every 3,300 molecules of water is going to be an HDO,
Uh-huh.
but I think it's something like 1 out of every 41 million is the D2O variety.
So when you're washing out
So
the
when-
deuterium-free water,
Yeah, so what,
it's not a big deal?
not a big deal because our water, the wastewater is about 180 parts per million, so it's nothing.
Okay.
Couldn't sell it as D2O, or it's not.
Thinking it's
gonna-
probably valuable.
No, not at all.
Okay.
no.
Any online questions? Any other questions from the audience?
So there's a question, water is life. Do you think water restructuring is also useful?
I have a theory on water that I haven't really shared publicly, but I will now. I think all water in the universe is one entity, one consciousness. So, and it exists in a partly non-local state. So all water is connected. Every water molecule is connected to every other water molecule. So when someone says restructuring water, I need a more detailed question. Because yes, you can restructure water with your thoughts. You can restructure water with a vortex. But what is the denotation and what is the connotation here? You know, and they're going to be different based on what the person wants to know. But if you look at structured water in the body, it's water that's pure, right? Molecularly pure, just like inside our mitochondria. It's water that it's just pure H2O. There's no other ions, contaminants, there's no deuterium or reduction of it. So when a water is in that pure form, it naturally takes on a crystalline structure. And that's quite an amazing phenomenon because you have this metabolic water in our bodies that it behaves like a solid, like a crystal solid, but it's liquid. So there's so much we still don't know about water. But again, I think all water in the universe is one consciousness. It's all one entity, you know, like the aspen trees, where you think you're seeing a bunch of trees, but it's really one organism. So I think all water is like that. I don't have any proof for that, but that's just my hypothesis.
Question for Jennifer. So after this conference, what is the next thing or things that you plan on doing at your place?
First, we're going to put a roof on my greenhouse because right now it's just a big pit. And then if everybody's still alive and hasn't killed me yet, then I think we'll probably look to see if Jeremiah's Tesla turbine has a place in our little closed loop system, and if it's available. I will be eagerly looking at Mike's generator plans to see if that moves forward, because that's a nice little gap filler. And then I think I might take up a hobby that includes reading a little bit more about this electric universe. It's pretty cool.
Jeremiah, do you want to explain the low-hanging fruit application of the Tesla turbine in Jennifer's application?
The low-hanging fruit application?
For her home.
What's the simplest use of the Tesla turbine just right off the bat in a off-the-grid home? How do you see that
The
playing out as the
easiest-
simplest?
The
Yeah.
easiest way to apply it at this point, as far as what we've developed.
Because
for-
they also have a lot of solar tube collectors.
Oh, yeah.
And they can probably get more, so.
Yeah, I would say the solar heat tube collectors are the best, but you also want to make sure you get the ones with the copper insert inside the tube, because those can go at higher temperatures, and then you can heat your thermal mass up to higher temperatures and run the turbine at a little bit warmer temperatures, so you get more power density in your turbine. And one of the things I want to do is build a small thermal battery, maybe here in the shop or in the back, and then start to use those solar collectors to run some tests with the new turbine to see the efficiencies and power density with the lower temperature ranges that we want to work with. But definitely, it's practical to get the solar heat tubes with the copper insert with I think it's acetone inside that transfers the heat from the bottom to the top of the bulb. And so we have a large range of temperature capabilities to work with. And then also there's solar heat, there are concentrators. There's solar reflectors that can reflect onto those tubes. That's another idea that makes it really cheap. We just took a basic pipe, or concrete form, those circular concrete form pipes, cut them in half, stuck one of those bulbs on inside, and put some. We put some of that silver tape. It's for like ducting work and stuff, I think.
That aluminum foil tape.
Aluminum
Yeah.
foil tape, and we just put that on the inside, and our single vacuum tube was 4 times more powerful with less than like $20 worth of stuff.
We're planning on doing that, but then also one experiment that we're looking forward to is putting white sand in the tubes themselves, because evidently that holds the heat well into the evening. So that would work for our heating. I don't know how it would impact the Tesla, but.
I would probably do a white sand, but you still want the heat to be collected at the top. And also, if you want to do something like white sand, there's this paint called the blackest paint in the world or whatever. There's so many different black paints. I'd recommend putting that inside with the sand and mixing it up kind of, so that you absorb more of the spectrum of light from the sun.
Okay.
And apparently they can absorb like 99.99 plus percentage of light from the sun. So you definitely have something like that in there, and it would take an existing solar heat collector and turn up the efficiency. So they say, I guess the tubes by themselves off the shelf are like 40 to 60% efficient. I don't know the exact amount on that, but I think it's just because they need something that absorbs more radiation from the sun, which would be a simple black paint of some kind, or ash or something.
Yeah.
How come so many of them are showing this 90+%?
Maybe they are. I don't know. Maybe I've got the wrong information. Some of them probably, but the last ones that I looked at were 40 or 60%. It was double that, or triple that in some cases of regular solar.
But it's still 2.5 times.
Yeah, it's still
more
way
than
more power out
solar
of
electric.
the solar. Yeah, way more. My dad did an experiment where he took about the same amount of surface area, and he was trying to make hot water with the same principles so that he could store the hot water, and he said he barely got any heat out of that solar panel. Comparing that to what I was doing with my solar heat collectors, I had in a couple days I had heated up, I think it was a 400-gallon tank of water up to 200 degrees Fahrenheit. So that's something that would have just taken way more solar panels than he was using. So it's definitely a lot. It's way more energy, and
Yeah.
so. But if you want to increase it up to the, I don't know what they usually are, but if you want to increase it to up to like over 90%, I would say just put some kind of that, like that black paint. That absorbs way more light from the sun, and I'm sure at radiation, and I'm sure it would be you could easily achieve 90+% efficiency from it. But yeah, like I
Yeah.
said, I don't know. I haven't done a whole lot of research on the efficiencies of the solar heat tubes, and there's many different people who sell them, so that's probably why we're getting different numbers,
Yeah.
because there's many different products from different companies.
Well, we'll definitely put the reflector on, and we'll definitely experiment with how to make it as hot as possible for as long into the night as possible, because it's not a daytime problem, it's a nighttime problem as
Yeah.
you apply it to heat.
So yeah, definitely
yeah.
you would want to collect the heat from the tubes and then store them in through a heat exchanger into your mass, which I'm just going to use copper tubing in and out of the mass. And then to extract the heat, I'll have another copper tube running next to it. So when I want to cool it to run the turbine, I'll pump it through one tube, and then when I want to heat it up, I'll pump it through another tube. And I'll have more details on that soon. That's a project I'm really excited about because it's more practical than my water battery idea.
You're actually supposed to be up on the panel discussion with us. Where were you?
I was here.
We have one more question. Oh, sorry.
Yeah, go for it.
Do you think the global scaling theory will be useful in your water and stellar research?
I'm certainly fascinated by it. I'm going to look deeper into it.
Definitely, yeah, we think the scaling thing is important. Is where the counter space is, we think. And we're definitely going to look into getting some powerhouse motors built. Mike's got the template, and so we're going to look into building a couple Tesla coils right off the bat.
You start looking at that 1/r relationship and how prevalent it is throughout just our experience. It's one of those things hiding in plain sight, and it's just the root of scaling in concepts. You know, as above, so below kind of a conception. And the entire harmonic series comes out of it, et cetera. So I highly recommend Schauberger on this one if you get a chance to look at him.
And his son, too, is very...
Yeah, he's really, talk about water. Yeah,
Yeah.
right, exactly.
The global scaling, Dr. Rainer Viehweger, several years back. So this year it was a global scaling talk specific about the cardio rhythms, but the several years back was a more general presentation on global scaling. Yeah, if you remind me, I can get you a copy of that.
Excellent,
And
thank
then he can also put either of you in touch with, I think, Dr. Hartmut Mueller, who is the founder of global scaling. And so, and that presentation is also on emediapress.com. And if you're here in person, still everything on the catalog is 75% off until midnight tonight if you use that discount code. And if you're streaming, 60% off over 250 different books and videos on emediapress.com, and that expires at midnight. So take advantage of it. I don't think we've ever had a discount that big on any of that before. I have a question about the sun. So, you know, I was in and out of your presentation, so I'm not sure if you covered it, but, you know, you have the so-called 12-year cycle, kind of peaks and dips, and at this point, we're kind of at that 12-year low, and it seems like the sun has been going dead, and I guess recent with low sunspot activity. And it seems like it came back, and then there was one that tripled its size instantly just in the last week and a half, or whatever it is. Do you see, okay, and then as far as weather, you know, so it seems like it kind of gets cooler with the less sunspots here in Spokane and up in this area. It's been like perma-winter. We've had like 9 months where it was cold, and we've had no spring whatsoever. And there was, you know, a rainy April weather all the way up until the day before summer started, till June 20th. It was cold. And is this going to be going back up, or are we going to have one of these Maunder minimum kind of periods, or is the sun really kicking back in? Or where do you see that going?
It's just recently started its what they call ascension phase, which is that beginning of that 12, 11-year cycle. And I think we're only 2 or 3 years into that, so it's got to hit that peak, and that's about where your El Niños kind of kick in and the hurricanes. And so you might get some relief, you know, it depends on the El Niño, because that can suppress hurricanes. So it's tied to the trade winds. So, but yeah, the sunspot activity recently is definitely tied to all the crazy weather we've been experiencing. I'm pretty sure of that. So yes, I would say your sunspot activity directly tied to these changes. It changes the jet stream patterns. And so that brings on all types of change. And we don't have we haven't done the deep dive historically, but that's what has to be done to really understand the effects and the events that are going to happen tied to these cycles. So I think some people have done it before. Back in the 60s, a fellow from NASA looked at the ascension-descension phase and decided that he could predict about 6 years out, somewhat, just using that relationship. And nothing really came of it, but I think he went to work for the Farmer's Almanac. So I'm not sure.
One of the little side notes on that that's interesting is the general location of the sunspots occurs if you do a projection of the star tetrahedron. The vertices that are near the equator are like the average is where those vertices lie, and then it's the same with the Tropic of Cancer, Tropic of Capricorn, and then spot on. To talk about spot on, it's the red spot on Jupiter. It's exactly on the tetrahedral angle.
That's 19.5 degrees, right?
Right.
Yeah,
Mhm.
just like
It's
the volcano,
just on.
like Big Island volcano.
Right.
Yeah,
Right.
goes through every
About where
planet.
the hurricanes spin up, so in that zone.
Yep.
Now, when I'm looking at sunspot pictures on the internet, if I happen to be talking to Eric Dollard, he always asks me, where are they?
They kind of do this, they call it the dolphin effect as they move towards the equator. They tend to have a V towards the equator over time, over the 11-year cycle. So they start that. So we're starting to see that. It's starting to come. And that might be because of the bending. You know, we talked about the different vibrations of the tetrahedron. So you get a little bending in that relationship of the polygon, or the star tetrahedron he's talking about. So that could be what drives this change in the latitude of the sunspots forming, something like that. So that's what we're looking into.
Jeremiah, why don't you grab a chair and sit up here with me and share this mic? Any questions online and also about the Tesla turbine?
So we do have a couple more online.
Sure, go for it.
I live in the tropics and am looking for a way to cool my home without costly conventional air conditioning. Do you have any recommendations?
Who's that?
I know there's Tim that's here has a house in Costa Rica, and it's all solar passive cooling. I think if they look into these passive cooling methodologies, there's going to be a ton of Google results. You can see the diagrams of kind of how it's set up. That's pretty unconventional, but it's not something, so strange, and it's pretty common and it works. As far as a technology that's uncommon, as far as cooling, I remember years ago, I think it's still there, is that there's a kind of a sophisticated swamp cooler kind of methodology where it's kind of a closed system. The moisture doesn't get into the air, and the company was called Coolerado.
Nice.
And I think they're still online. It was really more for the industrial size, right? Industrial buildings right now. I don't know if they have smaller scale ones for residential homes, but it produced something like the same cooling for about 1/3 the cost of a regular air conditioner. That's unconventional. Well, it's a pretty cool twist. There's also some cooling effect. I can't remember what it was. You know what I think you looked at the same with the turbine. Go for it.
So all the air conditioning systems, they compress a gas and then they decompress a gas through a nozzle. So one thing that would be practical would be to decompress the gas through the turbine. So you get the same temperature drop through the turbine and through the nozzle that you normally would, but you're spinning the turbine up, and so you can draw electrical power from the turbine, which can then help run the compressor on the air conditioning system, and that would give you a savings in air conditioning. And that's something that we want to experiment with soon. We just have to move from the first step to the next step, and we're almost done with the first step. So we'll move into that realm soon too. Also, on the opposite, using a heat pump, I think it's possible to incorporate the Tesla turbine with a heat pump and get electricity from the same system. So. Yep. Yep.
Yep.
Was that a humid environment that they're writing from?
They said the tropics.
The tropics, okay. So you can't dig five 300-foot trenches because it just fills with water. Right.
Yeah. I mean, something low-tech that you could probably try, like, I don't know if it would work, is if you take the solar tubes closed-loop system that we have, which is designed for heat, but if you just cover it up and then run the sucker, it would just pull the cool, right? Like, it'd cool off the slab and radiate the cool if you had pipes that were under there and not inundated with water. Just that. Yeah. Yeah, use your radiant floor heating that goes out to the tubes to
Ground
draw
source.
in.
But it wouldn't be a complete waste because you don't completely cut off your energy usage, correct? You just get a huge savings.
Right, well, it would just be something, you would still be using energy, yeah,
So
absolutely.
yeah, you can totally use your solar heat collectors to put more heat where you want, just to make it.
Yeah, but if he's down in the tropics, he doesn't need the heat as much as he needs the cool.
Yeah.
So you'd probably be better off just taking doing the water under the ground and then
Well,
running it into a radiator with a fan.
But just
Better result.
with the Tesla turbine, this is another part of the system with a small temperature differential. If you have unlimited temperature differential, which like in the case with the ocean, all you need is a small temperature differential, or with the land where it's cool, and then the outside air where it's warm, you can have a constant, you can recover a constant energy, you get constant energy from that temperature differential, but it'll just be at a little bit less efficient. So you can do that with Tesla turbine running with like not necessarily ammonia, but other gases that boil at lower temperatures. You can use that in like the same as fluid as the drinking bird, how the drinking bird works. I forgot what gas that was, but just
Little
any
fluid
old
like that.
any old gas that boils at really low temperature. I mean, what you could dial it in and find the best gas for your temperature differential. Yeah, constant flow of power always coming in from that.
Is there another one? Okay. So I wanted to go back to the water as one body and the ether physics of that, because this is always tweaking I'm always doing this, like Paul says, when we talk about ether physics. So, so clouds, that cloud up there, if you ask scientists, they would say it's millions of pounds. But yet there it sits up in the sky. And the cloud, if it was a mechanical process, would just drop its water and then get smaller and smaller and smaller and smaller, and then that would be done. But that's not what happens. The cloud just builds and builds. And I know Eric talked about the sun as an etheric transformer. Well, maybe clouds are etheric water generators directly from the ether into the manifest. So you guys know ether physics. What do you think?
There's a concept called Cowling's dynamo. Giovanni Grigori explains that that's the natural, that's what Tesla coil is doing, but it's a natural process called Cowling's dynamo, and it's a self-organizing electrodynamo, and that's what's, so that's a natural.
That's the sun, right?
That's any type of
Oh,
vortex.
okay.
If you have a vortex, it's tied to a natural phenomenon of Cowling's dynamo. And he uses the Hamilton variation principle of stable versus unstable electric magnetic field relationships. And that's Hamilton, the same fellow that came up with the quantarians, by the way. You might add to that, maybe?
Well, I mean, this is where that we're starting to see that link between the classic electromagnetic diagram of the transmission line and spherical, like, the polar 3D representation of latitude and longitude, which is very interesting as far as a transformation, just purely mathematically transformation. It's the match is exact. So what's going on there?
Transmutation, yeah.
Yeah, but a mathematical transformation,
Right.
possibly into that realm where you start getting very,
From the unmanifest to the manifest.
Right, right. This whole, the Dr. Haralick, we had a bit of a discussion, and he was mentioning just one of the other characters that's pretty fascinating throughout this is David Bohm.
Yeah.
And his discussions on the implicate versus the explicate, and those considerations really kind of open up where the direction you're pointing, I think.
The unfolding and the enfolding.
Right.
I'll keep scratching my head.
Yeah, me too. Yeah.
Hi, guys. Jeremiah, first I had a question for you about, can a Tesla turbine be used in a liquid environment?
Well, yeah, it can. It would be a specially designed turbine. It wouldn't be the same as what you would use with a gas. The distances, spacing between the discs would be different, and then the rotor end plates on the sidewall would be different. It would take a little bit of experimentation. It's much easier. Are you talking like to pump a fluid or to get energy from a fluid?
Well, what I was thinking of using it as a liquid turbine, and I don't know if that's viable at all. Where you'd run liquid through the Tesla turbine.
Yeah, that's viable. That's viable.
Okay.
It would take a little bit of experimentation just to tune in the distances between the discs and the rotor and the sidewall. Yeah.
And then, do you think if we did the necessary experimentation, would it be a more efficient pump than a Pelton wheel?
I think it could be with
I
the
have
right
no idea.
engineering. I don't have as much experience with using a fluid to rotate a turbine, but I know that when you pump a fluid with the pump, and the pump is a turbine in reverse.
Yeah.
When you pump a fluid with the turbine, it's the most efficient pump that exists. And they use it in the oil fields and other applications,
They use it-
military applications, to pump fluid that has particulates in it that would normally very rapidly destroy a regular turbine.
Because there's no
But they just
direct,
seem to last forever.
because there's no direct impact, right?
Yeah,
With the Pelton
everything's
wheel.
done by viscosity, and they even put a mark on a blade like that wax mark that you use to like mark concrete or wood in construction and stuff. That wax, it's almost like a crayon. They
Yeah.
put some marks on the blades of the pump, and the mark was still there after months of usage.
Wow, wow. Oh, that's because
Maybe the boundary layer.
and also the traction, the water moves slow against the face, but it drags, or the pump drags, either way, whichever way is going, it drags the fluid, and
Fluid
then
along with it.
there's that
Yeah.
shear, as you get closer and closer to the center of the space between the veins, yeah.
Yep.
Yeah, then I had a question for you, Jennifer, is, I was thinking about, the Pelton wheel, I know Pelton wheels are, as far as water is considered, fairly efficient, but I don't know if it's efficient as a Tesla pump or a Tesla turbine run the right way. And then my next question was, are you guys going to have to put off your hydraulic energy production because of the
The wipeout.
the wipeout? Yeah, right. And focus on your other areas first, and then get to that next year or something. What's your guess on that with you and your hubby?
Well, let me speak for him. No, I'm kidding. I think the hope is we can address it this fall.
Mm-hmm.
In terms of what that looks like, I don't know. It's like going down there is like this. It's 400 feet, but at probably 200 feet vertical drop.
Yeah.
And it's not fun to get things down there, and it's not fun to get things up.
No.
So.
What a hell of a head.
But we do have teenagers, and they can move rocks. So I'm thinking, I've got a hope for this fall, but I want to get some of the other more controllable things up first, and then that will be a stretch goal.
Yeah, yeah.
We're about a month and a half out before I start working on that.
Okay, but, so it sounds like you do have plans for this year. Okay.
He got an excavator. He got an excavator, and,
Yeah,
you know,
right, and it's gonna be
you got to use it, right?
yeah, and then you gotta put, it looks to me like you've gotta put a trench beside the creek far enough away so you don't have to worry about erosion
Well, the problem is that I actually can't get the excavator down there right now.
because of the trees and so on, and what
Because
happened?
it's a 450-foot drop, and it's, I'd say it's roughly about a 60-degree incline.
Oh my,
So it's tough. I mean, Aaron, I dragged him down there when he was out there, and he was chugging water when he got to the top. So it's pretty tough. So 90% of what I'm doing now is all by hand.
oh yeah, I can see how that could be.
So little
No.
by little.
Well, with a 400-foot head, more than a 400-foot head.
That's not the head, that's to get into the ravine.
Oh, okay, okay. I was.
It was a battle.
Yeah.
Yeah.
I wish it was a 400-foot head, but it's only, 450 feet to get down into it. The head is actually only about 30 feet.
Okay, because what I was thinking is, do you need to bury the pipe if there's water constantly going through it? Because moving water does not readily freeze.
It wasn't about freezing the water in the pipe, it was more about protecting the pipe from the water going over.
Yeah, right.
So our next goal is to actually walk the pipe up and over the side of the stream, or the ravine, I guess.
Right.
But that's a lot more trench work, a lot more moving trees and rocks and stuff like that, so.
Yeah. Because I had this notion that may be foolish, is how much of it could you lay on the surface of the ground? That's what I was wondering. Yeah.
Well, if it's not in the stream, I can lay it all in. I don't have to worry about it at all.
Okay.
Because the rushing water will not allow the water to freeze in that pipe.
Yeah, I mean, unless it's like 25 below, and I don't think you get.
Even that,
Really?
it won't.
Wow,
It will not
nice.
freeze in that pipe. As long as the pipe is full, it will not freeze.
Sweet, okay, thank you.
Should I be sitting up there, or?
By all means.
Grab a chair.
Grab a chair.
This question's for Jeremiah. I don't know how I missed it, but in your current thermal exchange system there. How much temperature delta between the hot and the cold side?
The test that we did here was about 150 degrees.
Mhm.
But the crazy thing is I did a test at 160 degrees, and I was getting 50 watts of power with my last turbine. This turbine has a larger inlet, so I'm actually getting more power out of the smaller temperature and pressure differential and getting more centrifugal head, which is actually making it more efficient than my last one. But I went from 160 degrees to 212 degrees. And with 160 degrees, I was getting 40 or 50 watts. And then with a 50 degree increase in temperature, I was getting 400 watts. So with just a really small temperature increase, I was getting about 8 times the power.
So what's the next diameter you're going to scale up to?
The next diameter is the 6-inch turbine.
6-inch.
And this is the one that I believe I can get all the centrifugal head I need to get Tesla's self-regulating condition, which simplifies the entire thing.
Got it. Thank you.
Something that normal turbines can't do.
Yeah.
They can't self-regulate like this.
What was that last word you said, Jeremiah, self-what?
Self-regulate. It keeps itself from going too fast and also keeps the gas, when you're not drawing a load, from going straight through the turbine. So it cuts off its own supply until you add a load, and then you start to see the boundary layer go from concentric circles down to more like the Fibonacci spiral when you're drawing a large load. If you draw too much load, then you start to lose efficiency, and your gas coming out of the turbine starts to heat back up. So that's why at these temperatures that I'll be running this turbine, I need to make sure that in order to get the efficiency and find out how many watts that we can continuously put out, we need to do all the testing for that. But I'm very confident with 280 degrees that we'll be able to get plenty of power very efficiently with this new turbine.
Hey, this is a question for Jeremiah. I got a question on your turbine. The spacers I noticed were all around, except for you had one that was a star spacer. And I thought that was in the first turbine that I saw, and I was wondering if there was a reason for that one, because I've never seen one with the star spacer in the middle at all.
So the star spacer is, I forgot the patent number, but the star spacer is from Tesla's improved rotor.
Oh, it was.
For the turbine, and it's a new patent, one of his new later patents.
Okay.
That he patented. So I've just been using that patent because it was his latest rotor patent.
Did you get a better readout from that one versus the old one, or did it work better?
It seems to be more structurally strong.
Okay, structural issues.
I actually haven't built the old ones because, I've just stuck with his latest rotor design.
Okay.
For as far as the geometry and the exhaust holes. And the biggest thing that I've been experimenting with is the nozzle and the disc spaces between the discs.
Okay.
And researching about his work and stuff. So.
Great. Thank you.
For the guy that's overheating in the tropics, he should look into the Isaac solar ice maker. It produces, per 1 square meter of reflector, produces about 5 kilograms of ice, and it uses the ammonia water absorption cycle. So it heats up the ammonia in the day and cools it down, or refrigerates it at night. And per square meter, it produces, on a sunny day, 5 kilograms of ice. So, yeah.
Nice.
That'll keep you cool.
That's cool.
We had 2 quick questions online. One, is the sun a different color than it was 10, 20, 50 years ago?
I'm not sure about that.
I've heard a lot of people say that, from observation. It's not in our wheelhouse right now, but yeah.
Could be the atmosphere is a different color.
Hmm?
Maybe the atmosphere is a different
That's
color.
right. That's right. See, right.
And then last question, your thoughts on how copper affects water?
Oh, well, is that for me? Anybody? I certainly wouldn't want to get metal copper ions in my water. So,
There is some copper colloidal mixtures out there. If you take too much zinc, it'll deplete the copper in your body. So you take the copper and zinc together. It's like 2 micrograms to however much zinc. But other than that, I don't know.
yeah, make sure it's
specifically
make sure it's copper 1. So,
Yeah, it's got to be the right form.
right form.
And then, so finally with Victor, Jennifer, Jeremiah, David, Bruce, give them a round of applause, please. And thank you so much for coming and being a part of this.